Hello, I am Pramod Prasad from EMC Education Services. Welcome to this online learning session in which I will present an introduction to Network Attached Storage or NAS. NAS is a file-level data storage that is connected to a computer network to provide file data access to a heterogeneous group of clients. In this session, I will talk about what NAS is, its components, NAS protocols, and how NAS is implemented. So what are the objectives of this session? Upon completion of this session, you should be able to describe NAS, its benefits and components, discuss NAS file sharing protocols, describe different NAS implementations, and describe file level virtualization. File sharing environment. Let's begin by understanding the concept of file sharing. File sharing, as the name implies, enables users to share digital files with other users. In a file sharing environment, a user, typically the creator or owner of a file, provides other users with access to the file. The file owner controls changes to the file and determines the type of access to be given to other users, such as read, write, execute, append, delete, and so on. In a scenario where multiple users try to access a shared file simultaneously, a locking scheme typically maintains data integrity and at the same time makes this sharing possible. Some examples of file sharing methods are File Transfer Protocol or FTP, Distributed File System or DFS, Network File System or NFS, and Common Internet File System or CIFS, and also the peer-to-peer or P2P model. FTP is a client-server protocol that enables data transfer between an FTP server and an FTP client. The client and server communicate with each other using TCP as the transport protocol. A distributed file system or DFS is a file system that is spread across several hosts. A DFS is simultaneously mounted on multiple hosts and uses a uniform naming convention. Provides hosts with direct access to the entire file system, and remote files are accessible as if they were locally available. NFS is a distributed file system protocol that enables files to be shared transparently between heterogeneous hosts. CIFS is an application layer protocol that also enables files to be shared between heterogeneous hosts. CIFS uses a command-based request-response mechanism for file sharing. Peer-to-peer or P2P file sharing model uses a peer-to-peer network. P2P enables client machines to directly share files with each other over a network. Clients use a file sharing software that searches for other peer clients. This differs from client-server model that uses file servers to store files for sharing. File sharing technology evolution. The figure on the slide depicts how file sharing technology has evolved over time. Traditional methods of file sharing involved copying files to a portable media such as a CD, a DVD, or a USB flash drive and delivering them to other users. This approach is not suitable in a scenario in which a large number of users at different locations need access to common files, such as in an enterprise environment. Network-based file sharing provides the flexibility to share files over long distances among a large number of users. File servers use client-server technology to enable file sharing over a network. To address the tremendous growth of file data in enterprise environments, organizations may deploy a large number of file servers. These servers are either connected to a direct attached storage or DAS, or a storage area network or SAN attached storage. This may result in the proliferation of islands of overutilized or underutilized file servers and storage systems. In addition, such environments have poor stability, higher management cost, greater complexity. Network attached storage or NAS emerged as a solution to address these challenges. What is NAS? NAS is an IP-based dedicated high-performance file sharing and storage device. A NAS device is essentially a compute system that provides only file-based data storage services to other devices over an IP network. A NAS device has its own operating system and integrated hardware and software components to meet specific file service needs. Its operating system is optimized for file I/O and therefore performs file I/O better than a general purpose server. As a result, a NAS device can serve more clients than general purpose servers and provide the benefit of server consolidation by eliminating the need of multiple file servers. NAS also consolidates the storage used by the clients onto a single system, making it easier to manage the storage. NAS uses network and file sharing protocols to provide access to the file data. These protocols include TCP/IP for data transfer and CIFS and NFS for network file service. NAS enables both Unix and Microsoft Windows users to share the same data seamlessly. General purpose servers versus NAS devices. A NAS device is not designed to be a general purpose server and also typically does not have a keyboard or a display unit. It is managed over the network, typically through a web browser. A NAS device is optimized for file serving functions such as storing, retrieving, and accessing files for applications and clients. As shown in the slide, a general purpose server can be used to host an application since it runs a general purpose operating system. Unlike a general purpose server, a NAS device is dedicated to file serving. It has a specialized operating system dedicated to file serving and uses industry standard protocols. Benefits of NAS. Some of the benefits of NAS are listed on the slide. Improved efficiency. NAS delivers better performance as compared to a general purpose file server because NAS uses an operating system that is specialized for file serving. Improved flexibility. NAS is compatible with clients of both Unix and Windows platforms by means of industry standard protocols. NAS is flexible and can serve requests of different types of clients from the same data source. Centralized storage. NAS centralizes data storage to minimize data duplication on client workstations and ensures greater data protection. Simplified management. NAS provides a centralized console that makes it possible to manage file systems efficiently. Scalability. NAS scales well with different utilization profiles and types of business applications because of the high performance and low latency design. High availability. NAS offers efficient replication and recovery options, enabling high data availability. NAS uses redundant components that provide maximum connectivity options. A NAS device also supports clustering technology for failover. Security. NAS ensures security, user authentication, and file locking with industry standard security schema. Low cost. NAS uses commonly available and inexpensive Ethernet components. And finally, ease of deployment. Configuration at the client is minimal because the clients have required NAS connection software built into them. Components of NAS. A NAS device has two key components, a NAS head and storage. In some NAS implementations, the storage could be external to the NAS device and shared with other hosts. The NAS head includes the following components. First, CPU and memory. Second, one or more network interface cards or NICs which provide connectivity to the client network. The network type could be Gigabit Ethernet, Fast Ethernet, ATM, or FDDI. Third, an optimized operating system for managing the NAS functionality. The OS translates file level requests into block storage requests and further converts the data supplied at the block level to file data. Fourth, NFS, CIFS, and other protocols for file sharing. And finally, fifth, industry standard storage protocols and ports to connect and manage physical disk resources. The NAS environment includes clients accessing a NAS device over an IP network using file sharing protocols. NAS file sharing protocols. Most NAS devices support multiple file service protocols to handle file I/O requests to a remote file system. As discussed earlier, CIFS and NFS are two common protocols for file sharing. NAS devices enable users to share file data across different operating environments and provide a means for users to migrate transparently from one operating system to another operating system. Common Internet File System. Common Internet File System, or CIFS, is a client-server application protocol that enables client programs to make requests for files and services on remote computers over TCP/IP. It is a public or open variation of the Server Message Block or SMB protocol. The CIFS protocol enables remote clients to gain access to files on a server. CIFS enables file sharing with other clients by using special locks. File names in CIFS are encoded using Unicode characters. CIFS provides the following features to ensure data integrity. First, it uses file and record locking to prevent users from overwriting the work of another user on a file or a record. And second, it supports fault tolerance and can automatically restore connections and reopen files that were opened prior to an interruption. The fault tolerance features of CIFS depend on whether an application is written to take advantage of these features. Moreover, CIFS is a stateful protocol because the CIFS server maintains connection information regarding every connected client. If a network failure or CIFS server failure occurs, the client receives a disconnection notification. User disruption is minimized if the application has the embedded intelligence to restore the connection. However, if the embedded intelligence is missing, the user must take steps to re-establish the CIFS connection. Users refer to remote file systems with an easy-to-use file naming scheme. It typically includes providing the server name and the name of the shared folder containing the files. Network File System. Network File System, or NFS, is a client-server protocol for file sharing that is commonly used on Unix and Unix-like systems. NFS was originally based on the Connectionless User Datagram Protocol, or UDP. It uses a machine-independent model to represent user data. It also uses Remote Procedure Call, or RPC, as a method for inter-process communication between two computes. The NFS protocol provides a set of RPCs to access a remote file system for the operations such as searching files and directories, opening, reading, writing to and closing a file, changing file attributes, and modifying file links and directories. NFS creates a connection between the client and the remote system to transfer data. NFS versions 3 and earlier are stateless protocols, which means that there is no table to store information about open files and associated pointers. Therefore, each call provides a full set of arguments to access files on the server. These arguments include a file handle, reference to the file, a particular position to read or write, and the version of NFS. Currently, 3 versions of NFS are in use. NFS version 2 uses UDP to provide a stateless network connection between a client and a server. Features such as locking are handled outside the protocol. NFS version 3 is the most commonly used version and uses UDP or TCP. It includes some new features such as a 64-bit file size, asynchronous writes, and additional file attributes to reduce refetching. NFS version 4 uses TCP and is based on a stateful protocol design and offers enhanced security. The latest NFS version is 4.1. NAS I/O operation. File I/O is a high-level request that specifies the file to be accessed. For example, a client may request a file by specifying its name, location, and other attributes. The NAS operating system keeps track of the location of files in the disk volume and converts client file I/O into block-level I/O to retrieve data. The process of handling I/Os in a NAS environment is as follows. In step 1, the client packages an I/O request into TCP/IP and forwards it through the network stack. The NAS device, or namely the NAS head, receives this request from the network. In step 2, The NAS device converts the I/O request into an appropriate physical storage request, which is a block level I/O, and then performs the operation on the physical storage. In step 3, when the NAS device receives data from the storage, it processes and repackages the data into an appropriate file protocol response. Finally, in step 4, the NAS device packages this file response into TCP/IP and forwards it over the network to the client. NAS implementation. There are 3 main NAS implementations. These are Unified NAS, Gateway NAS, and Scale-out NAS. Let's look at them individually. Unified NAS. The Unified NAS consolidates NAS-based and SAN-based data access within a unified storage platform and provides a unified management interface for managing both the environments. Thus, Unified NAS performs file serving and storing of file data, along with providing block-level data access to hosts that require it. It supports both CIFS and NFS protocols for file access, as well as iSCSI and FC protocols for block-level access. Due to consolidation of NAS-based and SAN-based access on a single storage platform, Unified NAS reduces an organization's infrastructure and management costs. Unified NAS Connectivity. A unified NAS contains one or more NAS heads and storage in a single system. NAS heads are connected to the storage controllers, which provide access to the storage. These storage controllers also provide connectivity to iSCSI and FC hosts. The storage may consist of different drive types such as SAS, ATA, FC, and flash drives to meet different workload requirements. Each NAS head is a unified NAS, has front-end Ethernet ports which connect to the IP network. The front-end ports provide connectivity to the clients and service the file I/O requests. Each NAS head has back-end ports to provide connectivity to the storage controllers. iSCSI and FC ports on a storage controller enable hosts to access the storage directly or through a storage network at the block level. The figure on the slide shows FC hosts connecting to the unified NAS over FC SAN, iSCSI hosts connecting over an iSCSI SAN, and NAS clients connecting over Ethernet. Each front-end port connects to the corresponding network type, providing access to appropriate data. Gateway NAS. A gateway NAS device consists of one or more NAS heads and uses external and independently managed storage. Similar to Unified NAS, the storage is shared with other applications that use block-level I/O. The management functions in this type of solution are more complex than those in a Unified NAS environment. This is because there are separate administrative tasks for the NAS head and the storage. A gateway NAS solution can use direct attached storage arrays or use the F3 infrastructure such as switches and directors for accessing SAN attached storage arrays. A gateway NAS is more scalable as compared to a unified NAS because the NAS heads and the storage arrays can be independently scaled up when required. For examples, NAS heads can be added to scale up the NAS device performance. When the storage limit is reached, it can scale up adding capacity on the SAN independent of NAS heads. Similar to a unified NAS, a gateway NAS also enables high utilization of storage capacity by sharing it with the SAN environment. Gateway NAS connectivity. The slide shows a gateway NAS system in which the storage array is shared between application servers and a NAS gateway over a traditional FC SAN. To deploy a gateway NAS solution, factors such as multiple paths for data, redundant fabrics, load distribution, and so on must be considered. Scale-out NAS. A scale-out NAS implementation uses a collection of nodes wherein each node may consist of either a NAS head or storage or both. The scale-out NAS implementation pulls multiple nodes together in a cluster. The cluster performs a NAS operation as a single entity. Scale-out NAS provides the capability to scale resources by simply adding nodes to a clustered NAS architecture. The cluster works as a single NAS device and is managed centrally. Nodes can be added to the cluster when more performance or more capacity is required. This can be done without causing any downtime. Scale-out NAS also provides the flexibility to use many nodes of moderate performance and availability characteristics to produce a total system that has better aggregate performance and availability. It also provides ease of use, low cost, and theoretically unlimited scalability. Scale-out NAS creates a single file system that runs on all nodes in the cluster. All information is shared among nodes, so the entire file system is accessible by clients connecting to any node in the cluster. Scale-out NAS stripes data across all nodes in a cluster along with mirrored or parity protection. As data is sent from clients to the cluster, the data is divided and allocated to different nodes in parallel. When a client sends a request to read a file, the scale-out NAS retrieves the appropriate blocks from multiple nodes, recombines the blocks into a file, and presents the file to the client. As nodes are added, the file system grows dynamically and data is evenly distributed to every node. Each node added to the cluster increases the aggregate storage, memory, CPU, and network capacity. Therefore, cluster performance also increases. Scale-out NAS connectivity. Scale-out NAS clusters use separate internal and external networks for back-end and front-end connectivity respectively. An internal network provides connections for intra-cluster communication, and an external network connection enables clients to access and share file data. Each node in the cluster connects to the internal network. The internal network offers high throughput and low latency and uses high-speed networking technology such as InfiniBand or Gigabit Ethernet. To enable clients to access a node, the node must be connected to the external Ethernet network. Redundant internal or external networks may be used for high availability. The slide provides an example of scale-out NAS connectivity that uses InfiniBand for the internal network connectivity. In this slide, we see a use case that illustrates how a NAS device or a NAS environment enables consolidation of file servers. Traditionally, network file systems for Unix and Microsoft Windows are housed on separate servers. This requires maintenance of both the environments. By implementing NAS, both Windows and Unix file structures can be housed together in a single system, while still maintaining their integrity. Using NAS, the same file system can be accessed via different protocols, either NFS or CIFS. The integrity of the data and security structure is still maintained, as long as the applications used for both methodologies understand the data structures presented. This slide provides another use case that shows how storage resources in a traditional file server environment can be consolidated using NAS. Separate file servers are replaced by a single NAS head, and all the storages used by the clients are consolidated into a single storage system. File level virtualization. A network-based file sharing environment is composed of multiple file servers or NAS devices. It might be required to move the files from one device to another due to reasons such as cost or performance. File-level virtualization implemented in NAS or the file server environment provides a simple, non-disruptive file mobility solution. File-level virtualization eliminates the dependencies between the data accessed at the file level and the location where the files are physically stored. It creates a logical pool of storage, enabling users to use a logical path rather than a physical path to access the files. A global namespace is used to map the logical path of a file to the physical path names. File-level virtualization enables the movement of files across NAS devices, even if the files are being accessed. File-level virtualization is implemented by using a virtualization appliance, which is a dedicated compute system that acts as a central virtual mount point through which all clients can access files. This slide provides a comparison of a file sharing environment before and after implementing file-level virtualization. Before virtualization, each host knows exactly where its file resources are located. This environment leads to underutilized storage resources and capacity problems because files are bound to a specific NAS device or file server. It may be required to move the files from one server to another server because of performance reasons or when a file server fills up. Moving files across the environment is not easy and may make files inaccessible during the file movement. Moreover, hosts and applications need to be reconfigured to access the file at the new location. This makes it difficult for storage administrators to improve storage efficiency while maintaining the required service level. File-level virtualization simplifies file mobility. It provides the user or an application independence from the location where the files are stored. File-level virtualization facilitates the movement of files across the online file servers or NAS devices. This means that while the files are being moved, clients can access their files non-disruptively. Clients can also read their files from the old location and write them back to the new location without realizing that the physical location has changed. So in this session, we covered NAS, its benefits and components. We covered common NAS file sharing protocols such as NFS and CIFS. We also covered 3 NAS implementations, Unified Gateway and Scale-out. Finally, we covered file-level virtualization. That brings us to the end of this session on Introduction to NAS. Thank you for watching.